All right, welcome to lecture 4.3 on right triangle trigonometry. We're going to be looking at the trigonometric functions in regards to right triangles. So we'll go ahead and look at our objectives here for this particular lecture, and it's to use right triangles to evaluate trigonometric functions. We're going to find the function values for some very common triangles, well, in particular right triangles, that will be used throughout this course. So we have the 30, 60, 90 triangle, which will cover both, I'm grabbing a pen here. The 30, 60, 90 triangle will cover both 30 degrees and pi over 6 and 60 degrees and pi over 3. And then we have the 45, 45 triangle, 45, 45, 90 right triangle as well, which is an isosceles triangle that we're going to look at. We'll use equal cofunctions of complements, so we'll learn what cofunctions of complements are and look at working with those, and then we'll solve just a couple of applied problems at the end. Okay, so we can see here that we start out with the idea of the unit circle. So going back to our previous information, and one thing that we learned when we took a close examination of the unit circle is that the length of the central angle, or the measurement of the central angle, is equal to the length of that intersected arc. And actually this wording off to the right did not translate properly. This should be pi divided by 3 radians. I don't know what happened to my division symbol, because I went straight from the notes, which has the division symbol in it. I guess when it did its conversion process, it messed with my equation editor stuff there. So that's pi over 3. That probably looks even worse than what it looked like just leaving it the way it was. All right, so here's the idea. We want to pick a point on the unit circle, and anywhere that you land on the unit circle, you can drop a line down to the x-axis and create this right triangle. And the unit circle is convenient to use because we know that the hypotenuse of this right triangle, which is the side opposite the right angle, so the hypotenuse of this right triangle will always be 1 because the radius of the unit circle is 1. So what we find when we look deeper into this is that we can calculate the trigonometric functions using the sides of the right triangles, and also calculating angle measurement as well. So let me fill in the blanks here for you. The figure to the left shows a right triangle that measures pi over 3 radians and an intersected arc of length pi over 3 radians as well. we construct the right triangle by dropping the line segment from point P perpendicular to the x-axis. So we see in this next figure down here at the bottom, we kind of have pulled that right triangle out of the unit circle now, and this is how we'll pretty much see it from here on out, as just the right triangle. This figure here is just naming the sides of the triangle, and we familiarized ourselves with this when we were talking about the unit circle, but it's worth mentioning again. So we have angle theta, which if it were still on the unit circle, that would be our central angle. And each of these sides of the triangle can be related to this angle theta here. Well, the hypotenuse obviously is always that side that is across from the right angle. And then the side that is touching the central angle, or angle theta here, is going to be adjacent to theta. And then we have the side that is opposite, or the leg of the right triangle that is opposite of angle theta, and we call that the opposite side, which should make complete sense. As mathematicians, we're not very imaginative when we name things. We usually try to name them for exactly what they are. So in general, trigonometric functions of theta depend only on the size of the angle and not the size of the triangle. So that's why we were able to make these same assumptions for this triangle, this right triangle down here at the bottom, that we would make if we were still planted in the unit circle there. So this first little mnemonic device that we run across this semester is very common when you're talking about trigonometric functions in regards to right triangles, and that is SOH-CAH-TOA, and I also introduced you to this idea during the unit circle lecture. So what SOH-CAH-TOA tells us are the relationships of the three basic trigonometric functions in regards to their side lengths. So sine is the S there, and that is opposite divided by hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And then there's even a little mnemonic device here. Some old hog came around here and took our apples. I have never heard this before. I've always just heard people memorize the SOH-CAH-TOA. And there's a cheesy little story about some Native American princess, SOH-CAH-TOA, that was built around it when I was back in high school, I believe. But I think it's easy enough just to remember the SOH-CAH-TOA, the lettering there, and that clues you in as what you need to as to what you need to divide to come up with that measurement. Okay, so just a little bit more on the right triangles here before we dig in and actually start calculating these things ourselves. I found this particular image in your textbook, and it just starts bringing together the idea of using the sides of the triangle to figure one of the trigonometric functions, and in this case it's tangent. And so from our little mnemonic device, SOH-CAH-TOA, we see that the tangent of angle theta is equal to the opposite over the adjacent. And so they're just showing you here, okay, so I've got angle theta, and my opposite side is side A, and my adjacent is side B. So the tangent of theta is A over B, which with the measurements of this particular triangle is 3/2 or 3 over 2. And then if you notice, these triangles are in proportion to each other. So if I multiply side A by 2, I end up with 6 for side A of the bigger triangle. Same thing with side B. If I multiply that by 2, I end up with side 4. And the reason I wanted to bring this into the lesson is because you can see that when you do the calculation of opposite over adjacent, so 6 over 4, it also reduces to 3 over 2. So that goes back to that statement that I made on the last slide that said trigonometric functions of theta depend only on the size of the angle, not the size of the triangle. So what I could safely assume here is that theta in the bigger triangle is equal to theta in the smaller triangle because the tangent of theta in both triangles is equal. And then this is just another example of that same phenomenon occurring. If we label a triangle down here with sides A, B, and C, A being the vertical side of, or the vertical leg, B being the horizontal leg of the right triangle, and C is always the hypotenuse. You really can flip-flop A and B, but C, 9 times out of 10, you're always going to see the hypotenuse called C. As a matter of fact, our Pythagorean theorem that says C squared equals A squared minus B squared, C has got to be your hypotenuse in this right triangle relationship as well. But like I said, however, A and B, that's debatable. You can flip-flop the 2 legs. But for our purposes, with this particular little bubble here talking about sine, cosine, and tangent, we'll look at side A as the opposite and side B as the adjacent as it relates to angle theta here in this particular triangle. So once again, this is just reiterating the SOH-CAH-TOA. So we have opposite over hypotenuse for sine, so A over C, adjacent over hypotenuse, and then of course the tangent we've already looked at in depth as well. So in general, my thetas are flying in the air here. In general, the trigonometric functions of theta depend only on the size of the angle, once again, the angle theta, and not the size of the triangle. You get so far, Roy? I'm kind of just blah-blahing at you right now. Excellent. Okay, and then we also have it in your notes. I put them side by side, but was not able to fit them accordingly on the PowerPoint slides here. But remember, your cosecant is the inverse of sine. So in your notes, it's listed right out to the side of it. And I'll just remind you the sine of theta here was A over C. So the inverse sine, which is the cosecant, is C over A. And secant goes with cosine. So the cosine of theta is given by B over C. And the inverse of cosine, which is the secant, is given by C over B. And then finally, we have the tangent, of theta, which in our drawing is given by A over B, and then the inverse cotangent is given by B over A. Once again, don't forget, it doesn't matter the size of the triangle, it matters the size of the angle theta that you're dealing with. Okay, so here we go. We are faced with the task of finding the value of the 6 trigonometric functions for this particular triangle. But before we can start doing the ratios, we have to find what C is. So we have to pull back that information from the Pythagorean theorem to, and oh my gosh, I wrote a squared minus b squared for the Pythagorean theorem. The Pythagorean theorem is a squared plus b squared. Sorry about that. So we have the Pythagorean theorem, and the Pythagorean theorem is a way to, Pythagorean theorem is a way to relate the sides of, I was wondering, I assumed that the square would have fixed, very sharp thinking there, Roy, because normally the squaring does take care of those negatives, but no, this is just me working on almost no sleep, and this being my 3rd lecture of the day, and I've already done, let's see, I've done 4 homework help videos with students today as well. So I'm lucky I'm even making half a bit of sense here. All right, so the Pythagorean theorem says that C squared is equal to A squared minus B squared. And if you're interested in the Pythagorean theorem, it is, there are tons of proofs of it online. There are even some really interesting visual proofs of it. So if you think about what A squared actually is, that's A times A. So if I took side A and multiplied it by itself, I would have the area of that square coming off of side A. And there's some really cool visual proofs that allow you to manipulate the areas that you've created, and you'll see if you pick up A squared to that square of side A and dump it onto the side C. So I'll just give you a quick idea here. So let's say that, and use your imagination on the square there. So this is A squared, and then some of the cooler little applets will let you actually break up B squared, and you'll see that it fits here, and when they're put together, you literally have a square of side C. So this whole thing together is C squared. So, you know, just some cool things out there to actually make it come to life a little bit instead of just be this theorem. But I've always thought the Pythagorean theorem was pretty cool. It's super powerful. You can do so much with it. Anyway, I'll stop rambling and actually use it like I'm supposed to be. So we have C squared here is equal to, oh, thank you, I wrote minus again. C squared is equal to 3 squared plus 4 squared. So A squared plus B squared. I guess I'm still in like hyperbola mode with the minus there. So C squared is equal to 9 plus 16. C squared is equal to 25. We don't have to take the negative into consideration here because there is no such thing as a negative length or distance, at least not in this dimension that I know of. Okay, I'm just going to clean up my triangle here. So we use the Pythagorean theorem to figure out that the length of side C is 5 units long. And actually, a 3, 4, 5 right triangle is a very common right triangle to use. It's one of the first ones you learn. And this is known as a Pythagorean triple. So we have 3, 4, 5, which is the Pythagorean triple. And just to remind you, your hypotenuse is always going to be your longest side. So you never have to guess, oh, which one's C? It's always going to be your longest side. All right, I'm actually going to clear this off so that I have room to calculate the trigonometric functions here. Okay, so I'm going to line them up with their corresponding inverse. So we have sine of theta, and its corresponding inverse is cosecant theta. We have cosine theta. Corresponding inverse is secant theta. And then finally we have tangent theta, corresponding inverse cotangent theta. And just to remind you, we have SOH-CAH-TOA. All right, so the sine of theta is the opposite over hypotenuse, and in this case, my opposite, and actually let me go ahead and label this triangle with opposite and all that. So here's my angle theta. This is my side that is opposite theta. This is my side that's adjacent theta. And then this is my hypotenuse. And we figured out that that's 5. All right. So for sine, I have opposite over hypotenuse, which is 3 over 5. For cosecant, I have the inverse, which is hypotenuse over opposite, or 5/3. For cosine, I have adjacent over hypotenuse. My adjacent is 4. My hypotenuse is 5. For secant, I have the inverse, which is hypotenuse over adjacent, or 5/4. Tangent, I have opposite over adjacent. Oh, let me be consistent here. I have opposite over adjacent, which is 3/4. And then cotangent is adjacent over opposite, or 4/3. All right, so I am assuming that you probably had all that done before I ever even began on it, Roy. Am I good to go forward? All right, great. Okay, so we have a right triangle here with a 45-degree angle. 45 corresponds to pi over 4 radians, and we found that out back in 4.1. We did a lot of work with trying to convert between radians and degrees there. The angle, radian angle is isosceles. So this is an isosceles triangle, meaning that I have 2 equal sides here. So you can see that the legs of my right triangle are the same. And so it has 2 sides of equal length there. And I want to go ahead and do the trigonometric functions for this 45, well, we know that this other angle is 45 as well, and then the right angle is 90. So we call this a 45, 45, 90 triangle. So let's go ahead and knock these out. So we've got the sine, and we'll consider this 45-degree angle theta. Okay, so the sine of theta and its partner, the cosecant. We have cosine with its partner, secant. Oops, there's where the E should have been. Can't get my pen back. There we go. Secant theta, and then the tangent. And I'll say this, with the 45, 45, 90 triangle and the 30, 60, 90 triangle, it's worth your time just to memorize these trigonometric functions with them, because this is the most basic right triangle, isosceles right triangle that you can have. Notice I have side length of 1, meaning this could be fixed back into the unit circle. Actually, I'm lying because the radius is square root of 2, but it's the most basic one. And then to build other triangles off of that, you would simply multiply each side by some factor, which we saw that back a few slides ago with looking at the difference in, you know, a triangle that had sides 3, 2, and then the hypotenuse, and you were getting the same tangent of theta as the legs of the right triangle being 6 and 4. So multiplying by a factor of 2 there. So if you can memorize this most basic one with legs of 1, you can extend that out into any of the any right triangle that fits this isosceles pattern, as long as you know the factor. And actually, when you're talking about the angle measurements, we've learned that it really doesn't matter how long the sides are. It comes down to the angle measurement there. So the sine of theta, let me write this at the top again. SOH-CAH-TOA. All right, so the sine of theta is opposite over hypotenuse. So we have 1 over the square root of 2. And cosine is adjacent over hypotenuse. Oh, let me stop here, because since we have 1 over the square root of 2, we actually need to rationalize that denominator. So I have 1 over the square root of 2. To rationalize that denominator, I'm going to multiply by a clever form of 1, square root of 2 over square root of 2. And I end up with square root 2 over 2. That's how you're going to see the sign given, square root 2 over 2. All right, and we see that the cosecant is the inverse of that. So I have the square root of 2 over 1, which just leaves me with the square root of 2 there. The cosine is adjacent over hypotenuse, so lucky us, that's 1 over the square root of 2. So we found out already that that is square root 2 over 2. And so secant is just square root of 2. And then we have the tangent, which is the opposite over the adjacent, or 1 over 1, which is 1. And once again, lucky us, the inverse is 1 over 1, which is 1. So there are all of your trig function values for an isosceles right triangle. 45, 45, 90. All right. You good to go, Roy? Excellent. Okay. So here we have the 30, 60, 90 triangle. So like I said at the very beginning, this is going to hit a 30-degree or pi/6 radian angle. And sorry, I didn't leave the blank to actually write it in there. This was already on the PowerPoint, so I figured I'd just leave it. Because I actually forgot to put the PowerPoint together until about 20 minutes before lecture, and I was scrambling. And then we have the 60-degree angle or pi/3 radians, so hence the 30, 60, 90 triangle. And the measure of the side opposite the 30-degree angle is 1/2 the measurement of the hypotenuse. So here we go. We're going to go ahead and figure out the functions for this. So sine of theta. And let's see, we want to do both the 30 and the 60 degrees. So welcome, Alicia. Glad to have you this afternoon. So we'll go ahead and do the 30-degree angle first over here, and then we'll, or actually, I think I have enough room to do it below. Then we'll do the 60-degree angle below. So we have sine, cosine, that's a theta, sorry, that looks terrible, and tangent, and then the inverses, cosecant, secant, and cotangent. All right, once again, so, TOA. All right, so we're going to start with the 30-degree angle. So I'm just going to label my triangle here. Obviously, this is the hypotenuse because it's opposite the right angle. This time, I have the vertical leg being adjacent because it's touching the 30-degree angle, and the horizontal being opposite for the 30-degree angle. And I'll just color code this and show that that's the pink one. Okay, so sine is opposite over hypotenuse, 1/2. No real work that we have to do there. The cosine of theta is adjacent, square root 3 over hypotenuse, 2. And the tangent of theta, or the 30-degree angle, is opposite over adjacent. However, we ended up with a root in the denominator. So 1 over the square root of 3. I need to multiply by my clever 1, which is square root of 3 over square root of 3. And so I end up with square root 3 over 3. So this is the same thing as square root 3 over 3. Uh-oh, I grabbed the wrong shade of pink, it looks like there. Looks very Valentine's-y on my page, so I'm proud of that. The little things in life that you have to enjoy. All right, so now we'll look at all of the inverses here. So the inverse of sine is cosine. So this is 2 over 1, which is just 2. Inverse of cosine is secant. So 2 over square root 3. Let's come off to the side here. 2 over the square root of 3 multiplied by square root of 3 over square root of 3. So I have 2 square root 3 over 3. So this is equal to 2 square root 3 over 3. And cotangent, I started out with 1 over the square root of 3, so that's just square root of 3 over 1, which is just the square root of 3. So there are your measurements for the 30-degree angle, or your trigonometric values, function values for the 30-degree angle. And now we're going to look at the 60-degree angle. So I'm going to change colors completely. Grab an orange here. So now theta is the 60-degree angle. Hypotenuse stays the same. It's always the side opposite the right angle. Now the horizontal leg becomes my adjacent, and the vertical leg becomes my opposite. Okay, so let me just write down my functions here. Sine of theta, cosine theta, tangent theta, and cosecant theta. Sorry if you can hear my dog barking out there. I have a dog and she's squirrel crazy, like literally squirrel crazy. And so she's, especially during the winter when all the leaves are off the trees because she can see them all, so she's out there just going crazy, barking at them. She got one the other day and ate it whole. Well, she didn't eat the whole thing. My husband pulled out the upper half of the squirrel torso from her throat, but she got the bottom half of it. All right, so sine of theta. So we have opposite over hypotenuse, square root of 3 over 2. No work has to be done there. Cosine is adjacent over hypotenuse, so 1 over 2. And I guess I kind of wrote that over the value. So let me just move this. I'm moving the letter in pieces. There we go. Adjacent. So that side is measured at 1. All right, and tangent is opposite over adjacent. So I have square root 3 over 1, which is just the square root of 3. Moving to the inverses, cosecant is the inverse of sine, so 2 over the square root of 3. And we already know what 2 over the square root of 3 is. That's 2 square root 3 over 3. 2 square root 3 over 3. Secant, 2 over 1, which is just 2. And cotangent is 1 over square root 3. And we found earlier that that's equivalent to square root 3 over 3. All right, Roy and Alicia, how's that for you so far? Roy says good. Alicia, I know you kind of came in after we had already dug in, but hopefully it's all making sense. Are you ready for me to move forward, Alicia? Okay, Alicia may have stepped away from her computer. I'm going to go ahead and move forward. Okay. Oh, I forgot I had given us actual slides to write all that out on, so we've already done all this work, so I'm just going to draw a big cheesy grin smiley face on this. And same thing here. Okay, So here we just have a chart showing us these common measurements for right triangle angles here. So this is just kind of that one-stop shop that you can come and look at. I also put this chart in your notes, so this would be a good one of those good pages to have available when you sit down to do the test. So it's just summarizing everything we just did. Okay, so two positive angles are complements of each other if their sum is 90 degrees, or 90 degrees is the same thing as pi over 2. And I'm just looking at your notes to see, okay, so I had a blank here, so that blank is pi over 2. Any pair of trigonometric functions, f and g, for which f of theta equals g of 90 minus theta. So this is just saying when you have a function of theta, it's going to be equal to 90 minus that function, or if you have that situation, and you flip-flop it and say g of theta is equal to f of 90 minus theta, these things are called cofunctions, and that's a blank on your notes right there. So if we look here with a right triangle, we know we have to block out that 90 degrees. The interior angles of any triangle equal 180, or the sum of the interior angles. So it should make sense that you have your right angle, you're going to add theta, and then you're going to add 90 minus theta, and that's going to total up to 180 degrees because your right angle is obviously 90 degrees. And then that means you've got 90 degrees left to split between the other two angles. So theta plus 90 minus theta has got to equal that other 90 degrees to total out to 180 degrees total there. And let me just look at your notes to make sure. Okay, yeah, we just have the cofunction identities, which is on the next slide. Okay, so here we have the cofunction identities. We're given that the sine of theta is equal to the cosine of 90 minus theta. And let's just take one of these cases and kind of wrap our brain around it. I'm not going to do it for all 6 of them, but I think sine and cosine would be good to look at here. So don't forget we have SOH-CAH-TOA. All right, so sine is opposite over adjacent. Okay, so if I have theta here in this corner, the sine, I put 2 I's in there, sorry. The sine of theta is equal to the opposite over the adjacent. Okay, so the cosine, let me get a different note.
Hey. Hello?
Hello, Alicia?
You said the sine is opposite of the adjacent? I thought it was the hypotenuse. Am I backwards?
Oh, I'm sorry. Yes, the hypotenuse. Thank you for stopping me. Thank you. I appreciate you jumping in there, Alicia. I thought you had accidentally hit your microphone and we were about to hear something we weren't supposed to hear. So sine is opposite over hypotenuse, which in this case is A over C. And that's for theta. And let me get a different color here for 90 minus theta. Okay, so we have 90 minus theta here. And the cosine of 90 minus theta, well, cosine is adjacent over hypotenuse. So we end up getting A over C as well. Okay, so do these cofunction identities now make sense? Especially now that Alicia caught me with putting the wrong function or the wrong denominator up there. Does it make sense now how these relate to each other? Y'all good? Okay, Roy says yes, and Alicia says yes. Great. So once again, this is one of those charts that you'll probably, either want to memorize or have handy, maybe include it on your little cheat sheet for when you go in to take your midterm. Okay, so now we're going to look at working with cofunctions of the same value. So we have that we start out with the sine. Let me write our SOH-CAH-TOA again. Apparently I need it more than y'all do because y'all are on top of this. All right. So we start with the sine of 46 degrees. And we're told, using our cofunction identities, that this is going to be the same exact thing as the cosine of 90 degrees minus 46 degrees. So if I want to write an equivalent cofunction, so a cofunction with the same value as the sine of 46 degrees, I simply do the subtraction there. So the sine of 46 degrees is the exact same thing as the cosine of 44 degrees, which is 90 minus 46 there. All right. The cotangent of pi over 12, well, we know from our trigonometric cofunction identities that the cotangent is equal to the tangent of 90 or pi over 2 minus that particular angle measure. So in this case, we have, this is the same thing as the tangent. 90 degrees is equivalent to pi over 2 radians minus pi over 12 radians. This one's a little bit trickier because you have to be able to do your fractional math. So we have the tangent. Okay, I need a common denominator to be able to subtract these two values. So I just need to multiply by my special form of 1, 6 over 6 for that first term. And I get 6 pi over 12 minus pi over 12. So this is the same exact thing as the tangent of 5 pi over 12. Are y'all cool with the cofunctions? Okay, Roy says yes. Oh, I just saw that you said, Alicia, you would have just heard kids. Okay. Okay. Can you say that again? Is everything clear for you, Alicia? I didn't see that you had asked me to say something again. Okay, good. We'll move forward then. Okay. Okay. Great. I just read what you typed in the chat window there. All right. So applications, angle of elevation and angle of depression. So this is just setting up the idea of what these things are here. This is not an actual problem to work. So an angle formed by a horizontal line. Let me get a color here. Angle formed by a horizontal line. And the line of sight to an object, so I have an object flying above and an object driving below in this particular picture, that is above the horizon. So if it's above the horizon, we're talking about an angle of elevation. That should make sense. If we're talking about below the horizon or below your line of sight, we're talking about an angle of depression. So not depression as in I'm very, very sad, but depression as in going down. So just okay. So we are given a problem here. We have this lake, and we're told the irregular blue shape in the figure represents a lake. I would hope that you would have known that before they stated it. The distance across the lake, A, so I'll just highlight the distance here across the lake, is unknown. To find this distance, a surveyor took the measurements shown in the figure. Okay, so they marked a spot on one side of the lake and on the other, and this is where your surveyor may have been standing. And by the way, y'all are being treated to my awesome artistic abilities this afternoon. So we have the horizontal line here, and if we can figure out that angle of elevation, which we know is 24 degrees, we can figure out the distance across the lake here. So we need to figure out what the sides that we're dealing with. So we know this is 750 yards, and that's going to be our adjacent side. We're trying to figure out our opposite side, so we want to use the trigonometric function that relates the adjacent and the opposite sides. Well, once again, SOH-CAH-TOA, we see that the tangent relates the opposite over the adjacent. Or we could use the cotangent, doing adjacent over opposite. It really doesn't matter. We'll just use the tangent since that's one of the basic functions instead of the inverse function. So we are aware now that the tangent of 24 degrees, so our angle theta here, is equal to opposite, which we don't know, A, over our adjacent side, 750 yards. And if we use a little bit of algebra, we figure out that we can multiply both sides of this equation by 750, and we'll divide out there with our common factors. And now we have, well, side A is equal to 750 times the tangent of 24 degrees. So this is where your calculator comes into play. And I did not check and make sure my calculator was set correctly. I do not have access to a calculator emulator on my computer because it's a Mac computer, and TI does not make an emulator that is compatible with Mac. But just so you know, if you want to check and make sure that your calculator is set, we want our calculator set in degrees here. You will press at the top of your calculator the mode button, and it'll tell you what your calculator is set in. Right now mine's set in radians, so I want to move it over to degrees since I'm calculating calculating using degrees instead of radians. And so when I put 750 times the tangent, and you've got a sine, cosine, and tangent button on your calculators, and then the second functions, let me write this out for you. So I have a sine button, and the second function looks like this. Sine -1, that's the inverse. So that's going to be your cosecant. Let me write that out. This is going to be your cosecant, that second function there. And we'll have a secant, and then we'll have a cotangent. Okay, so you have the sine button, the cosine button, and the second function there is going to look like cosine inverse. And then you'll have a tangent button and tangent inverse. So hopefully that helps you out with your calculator a little bit. But I just made sure I was in degrees. 750 times the tangent of 24. When I put that into my calculator, I end up with, and I'm going to use the wavy equal sign, approximately 333.9. So that tells us the distance across the lake, since I was solving for A there, the distance across the lake is equal to 333. I had it right the first time. 333.9, and this is in yards. 333.9 yards. Do either of y'all have any questions about that particular problem? Oh, calculator is plus your BFF. Get rid of the Mac? No, I would never get rid of my Mac. I adore my MacBook. Okay, Alicia, you gave me a red X. Was that a red X on the MacBook or a red X on you need more on this problem? Okay, great. So you're good to move on. Just give me a green check if y'all are both ready to move on. We've got one more problem to look at, and then I'll cut you loose. All right, good deal. Okay, so at a certain time of the day, the angle of elevation is 40 degrees. So we're looking at this angle right here, is 40 degrees. To the nearest foot, find the height of a tree whose shadow is 35 feet long. So basically, this is the same exact problem that we just looked at, but instead of looking at a lake, you're looking at a tree. So since this is our angle theta, H is our opposite, 35 is our adjacent. So we're actually going to use tangent again here. And we have the tangent of 40 degrees is equal to the opposite over adjacent. I'll multiply both sides by 35 to get that 35 out of the denominator. Divides out there. And I'm left with 35 times the tangent of 40 degrees equals H. And let me put that into my calculator. 35 times the tangent of 40. I am getting that the height of this tree is approximately 29.4 feet high. Did y'all get the same thing? Did y'all give this a try in your calculator? Okay, Roy says yes. Alicia, you've got kids running around, so I am assuming that you're probably not playing with your calculator. So did this make sense to you, Alicia? Uh-oh, we may have lost Alicia to the kids there for a moment. All right, so I'll just assume Alicia's okay. She seems to be pretty sharp with all this stuff. Alicia and Roy, once again, thank y'all so much for your consistency with showing up and your dedication to this course. It makes it so much easier to give a lecture when there are people there to give feedback and to catch my mistakes. I appreciate it very much so. Y'all have a wonderful afternoon. Have a wonderful weekend, and hopefully I'll just see y'all next week for lecture 4.4. Oh, yes, thank you, Roy. Yep, 4.4 is tomorrow, 4.5 is next week, or maybe the review is next week and then the test. So, yeah, I'll see you tomorrow, Roy. Thanks again. You too. Bye-bye.